Okay, good morning, everyone. This is going to be our presentation on centrifugal cleaning as part of our Advanced Topics in Paper Recycling course. And let's just get started. What we're going to talk about today is cleaning, and that implies centrifugal cleaning in a paper recycling mill. And what we're going to do is use rotational fluid flow and the forces that are generated in rotational fluid flow to impart forces on contaminants, and that will separate the contaminants from the fibers in many cases. Okay, centrifugal cleaning, its objective is to remove impurities from the pulp stream. And centrifugal cleaners can remove the following items: metals, inks, sand, bark, dirt as examples, and others, of course. And the key thing here is that these materials are of a density and all other characteristics that are different from paper-making fibers, and this will allow us to separate them from the fibers. Okay, so how does centrifugal cleaning work? In a centrifugal cleaner, we're going to use fluid pressure. So you're going to use a pump. We're going to pressurize the fluid, and that's going to force fluid into a centrifugal cleaner. What will happen is the fluid will rotate in a tapered cylinder, and that rotational fluid flow causes denser particles to move to the outside faster than lighter particles do. Good fibers actually, in many cases, don't go to the outside as fast as these denser particles, and they're actually stay towards the inside and oftentimes upward to an accept valve. Okay? And then the dirt that actually moves faster towards the walls goes downward and is removed oftentimes at the bottom in a rejects port. So basically, centrifugal cleaning is using centrifugal forces where a fluid is flowing and spinning, and the high density material is going to the wall at a certain speed, and the fibers are also going to the wall at a certain speed. And hopefully the contaminants are going fast and the fibers are going slow. And what happens is the fibers, for that reason, because they're going slower, stay in the middle, and the heavyweight contaminants go to the outside. We can use the same principle actually to separate fibers from low density material. In this case, the fibers are going relatively fast towards the wall, and the low density material is staying in the inside. Okay, there are three basic cleaner types. We call them high density cleaner, forward cleaner, and through flow cleaner. This is just a convenient way to think about them. High density cleaner separates very large, heavy contaminants such as rocks and glass. These high density cleaners are used right after pulping to get rid of very large contaminants. Contaminants that could be 40 millimeters in thickness. These cleaners are pretty large because they're upstream in the system, and they can be batch or continuous rejects flow, and I'll show you that later. Forward cleaners separate fine, heavy contaminants such as sand and inks. They're also called cyclones or hydrocyclones, or just cleaners. Their diameter is typically smaller than the high density cleaners, 70 to 400 millimeters. And then the through flow cleaner separates fine, light contaminants such as glues, adhesives, plastics, things like that. They're also called lightweight cleaners or reverse sometimes they're called reverse cleaners, but reverse cleaners implies a different flow. So I would actually just strike that reverse cleaners. Their diameters are 100 to 400 millimeters for the through flow. Okay. Now, some of the functional differences, I've listed the three cleaner there's actually 3 cleaners that we can also, a different kind of category, high consistency cleaner, that's the high density cleaner that I spoke of before, and then there's a medium consistency cleaner and a low consistency. So actually forward cleaners and through flow cleaners are both low consistency, and high consistency cleaners are the high density cleaners, and medium consistency are somewhere in between. You can see that the consistency for the high HC cleaner is around 2 to 4.5, and for the low consistency is 0.5 to 1.5. The centrifugal acceleration, that's the force due to the fluid flow spinning like this. The centrifugal acceleration for high HC cleaners is less than 60 Gs, where a G is the acceleration due to gravity. So the G is the acceleration of an object in the gravitational force field, and it's 9.8 meters per second squared on Earth. So the medium consistencies have a higher, MC cleaners have a higher gravitational force up to 100 Gs, and then the low consistency have a much higher gravitational force up to 1,000 Gs. And what this is telling us is that the HC cleaners to operate effectively don't need a lot of strong forces, and then as we go to the lower consistency, we're trying to remove smaller, finer particles, and they'll need more centrifugal forces to do the removal. And the reject rate by mass, the reject rate as measured in mass rejected as a percent for each stage. For the high consistency HC cleaner, we're around 1% reject rate. So we're only rejecting 1%. And the reason why is because we usually don't cascade these cleaners, and I'll talk about cascading later. Cascading is a way to save fiber. Medium consistency is the same thing. We have about 1% rejects. But the low consistency cleaners, LC, they can have a reject rate of 3 to 30%, meaning that we're going to reject maybe 20% of the solids coming into the cleaner. And we'll see that we use a cascaded method in order to save the fibers, and then it also helps us in our screening efficiency for that material, our cleaning efficiency for that material. Okay, so what does a centrifugal cleaner look like? As I said before, it's a tapered cone. And typically, this is a forward cleaner designed to remove heavyweight rejects. And here's the feed inlet, and the fluid comes in here, and it starts spinning around. And as the fluid spins around, the centrifugal forces, in part, act to throw the high-density contaminants to the side wall. And then the fibers also are moving towards the side wall. And that's an interesting point. Anything with a density higher than water will move towards the wall. So both fibers and contaminants are moving towards the wall, but the fibers don't move as fast as heavier, denser contaminants. So that's how the separation occurs. And so what happens then is that the material on the wall continues to spin around, and then it's rejected out this reject port. And then the good fibers, which are spinning, they actually turn direction, and they'll come back, and they will go out this accepts port. So mainly the fibers go this way, and mainly the contaminants go this way. It is, and I should remind everyone that it's a imperfect separation. So the separation is not perfect. So we always need to keep that in mind. Now this diagram on the right here kind of shows you the arrows and how things go. And it shows you the flow that's reversed out the accepts, and it shows you the rejects flow. Now if we go ahead and do a very crude animation, here again is our cleaner body. Here's our feed, accepts, and rejects port. And if I run the animation, we can look, and the black particle is an ink particle or a high density contaminant going out the rejects, and the orange somewhat fiber-like material there is the fiber. You can see it changes direction, it continues to spin, and then it goes out the accepts port. So one more time. And this just kind of gives you a feeling for what's going on here. Okay? All right. Now, cleaners, especially low consistency cleaners, I'm mainly going to be talking about low consistency cleaners to start off with. The low consistency cleaners can only handle a volumetric flow rate that's a small fraction of the total flow rate in a pulp mill, so in a recycle mill. So for instance, a cleaner might be able to handle 100 gallons per minute, whereas the total pulp flow is volumetrically might be 1,000 gallons per minute or 10,000 gallons per minute. So what we do is we put these cleaners into arrangements that are called banks, and these banks have individual cleaner bodies that are piped up like this. They all share an accepts header. So the accepts header, they share a feed header and a rejects header. So you see this feed header right here in the middle. It has it opens up to each cleaner tangentially, and it gets each fluid flow in there to tangentially spin. And so that feed header is shared by all these cleaner bodies. And then the cleaner bodies all have the accepts going to a common accepts header, and all the rejects are going to a common rejects header. Okay? And this is just a side view, and it's just showing again the feed header, the accepts header, and down here is the rejects header. Okay? And you can see that there's a row of cleaners to the left and a row of cleaners to the right. This is a picture I took at a recycle mill, and these are forward cleaners. And you can see that we have a row of cleaners here, and then there's another row of cleaners in the back here. This pipe right here is the header for the feed. This pipe right here is the header for the accepts. And then down here, what you notice is that you see that each of these cleaner bodies empties off. Now it empties off into a trough. And that trough right here collects all the rejects. You can see it squirting out kind of right here. And so that's our rejects header. So in this case, the cleaner rejects are at atmospheric pressure. The feed is at another pressure, a higher pressure, determined by a pump that's feeding these cleaners. And then the accepts is also pressurized, and that there is some type of valve that that adjusts the accepts pressure. And so one way that manufacturers explain to the paper recyclers how to run the cleaners is by specifying a feed pressure, an accepts pressure, and of course the reject pressure. Okay, cleaners also can be assembled horizontally rather than vertically. I think a key point here is that the forces in the cleaners, the centrifugal forces and the other forces in the cleaners are much, much greater than the gravitational force. So it's not, you can have cleaners that are upside down, that are horizontal, or are vertical and the rejects pointing down. It doesn't matter. So here in this bank, if we take a look, this port right here will be our feed port. This one right here, let me just get my bearing. This one right here is the rejects port, and this one right here is the accepts port. And you can see here's a cleaner, and here's the rejects, and then the accepts actually go out the top, and then this red part right here indicates the feed, and that's going to go into the cleaner. So cleaners can be set up in many different ways. The way they're set up typically depends on how effective the cleaner manufacturer wants to be in keeping the footprint of this cleaner small, cleaner bank small, and also cleaners are set up in different ways so that they are easier or harder to maintain. So for instance, if maintenance is an issue, for instance, you have to take cleaners down, you might want them to be where somebody could reach them from the floor. Or if they get plugged at the rejects, you might want to have the rejects accessible for unplugging. So maintenance and size of the footprint dictate quite a bit how these banks are arranged. Okay, now here this is a picture of a cleaner pump at a recycle mill, OCC recycle mill. Here's the pump right here, and here's the motor, and this is one of the people I've been working with. He's about 6 feet tall, so if you can tell, this motor is about 5 feet tall, huge motor. And then the pump right here might be 2 feet in diameter, 3 feet in diameter, maybe more. And so the point here is that the pump is actually consuming the energy, and that's where we're paying our bills. We're paying for pumping costs, and that's what's actually doing the separation. All right. Now, and I'm mainly talking here about LC cleaners, low consistency cleaners. Well, we said that they reject, for each stage, they reject maybe 20% of the material. And let's just take a look at how they are arranged in a cascaded fashion, and this is used to save fiber. Here's the feed to our cleaner system, and that feed is mixed with dilution water and another stream from the secondary cleaners. And that combination goes into our primary cleaners, where the centrifugal forces help us remove some contaminants. The accepts, the cleaner accepts, go out this way on through the process, and then the rejects that are hopefully enriched with the contaminants are rejected out the bottom of the cone here. That is mixed with dilution water and stream from the tertiary cleaners, and that goes to the secondary cleaners. Now the secondary cleaner's job is to save fiber. And so what it does is it's got a feed coming in here that's pretty dirty, that's relatively more dirty than the overall system feed. And it will try to enrich the contaminants here, and it will take some of the fibers up here. Now these, in each cleaner body, let's just assume it's an 80% accepts, 20% rejects split for fiber. And so what we'll see here is that 80% of the accepts going this way, 20% is going that way. And then of that, this one right here, 80% is going that way, 20% is going that way. Now the rejects from the secondary cleaners are mixed with a dilution, mixed with dilution water again, and then they're pumped to a tertiary cleaners. And I should mention that each bank of cleaners has a separate pump. And then the tertiary cleaners again reject some material and accept some material. And again, it's to save fiber. And what we realize here is that every 80-20 split, so 20% of the fiber is going that way, and then 20% of that 20% is going this way, and then 20% of that 20% is going this way. So every time we have another bank of cleaners, a secondary, tertiary, and systems can have quaternary and 5th stage and 6th stage, each time we're saving some fiber. And so the fiber flow in our rejects is getting smaller and smaller as we're going down this way. So for example, if we try to do a little simple simulation, here we have a 3-stage cleaner system. Here's our primary, secondary, and tertiary cleaner. And if we have 100, let's just say, pounds per hour of solids coming into the system, and this primary cleaner accepts 96 pounds per hour, then we know that the rejects in the entire system should be 4. And I can type in the number 4, enter, and it says you are correct. So basically we have 100 pounds of solids coming in, 96 accepted, 4 are rejected. And then we can take a look at maybe something else. Here, actually, when I said there was 100 pounds coming in this feed, we didn't really know what this stream was, because this stream is actually the sum of the accepts from the secondary cleaner and the actual feed to the entire system. So if our feed is 100 and then the solids flow rate from our accepts from our secondary is 20, then obviously this stream is 120. So we have 120 pounds per hour going to this cleaner stage. And then I'll hit enter, and it says yes, you're correct. So 100 plus 20, it does equal 120. That's great. And then we can continue on. Let's see what the next one is. So I've already done that one. And I've done that one. on that one. Okay, so then we can just go on to this one. If we look at this cleaner body, if 120 pounds per hour of solids is coming in and 96 is accepted, then the answer should be 24 being rejected from the primary cleaner, and that's correct. And so I have to be careful when I press these buttons. Okay, and then now we have 24 being rejected by the primary and 10 being accepted by the tertiary. So you see the oven dry mass flow going into the secondary cleaner is going to be the just addition of these two, which happens to be 34. And still we're correct. That's good news. And then let's see if we get the next one. All right, now around the secondary cleaner, we have 34 going in, 20 being accepted, so 14 pounds per hour of the solid material should be rejected. And it says, great job, end of exercise. Now, if we kind of take a look at this, what we see is that 100 pounds per hour is coming in, and by the time we get to the feed for the primary cleaner, it's 120. 96 is being accepted, and then the reject is 24, and then the feed to the secondary is 34, and then actually the feed to the tertiary is 14. So you see that the feed to the primary is much greater than the feed to the secondary, which is much greater than the feed to the tertiary. And that brings me to another point. When you go to a recycle mill, what you will see is your primary bank of cleaners, there might be, let's say, 100 of them, because they have to take the highest flow rate. And then for your secondary bank, there might not be 100, there might be only 60. And for your tertiary bank, because that's a smaller flow, instead of 60, there might only be 30. And then if you have a quaternary, it might only be 10. And then a fifth stage might only be 4. And a sixth stage might only be 1. So you can see that as you go in your stages, the primary stage has the most, and then the secondary has maybe less and less and less and less. Okay, now, why do we have to have this 80-20 split? Okay, now the reason why is because of this graph. If we take a look at this graph, it's what we're going to have on the x-axis is the reject ratio. The reject ratio is the mass flow, oven dry mass flow of rejects divided by the oven dry mass flow of the inlet. Okay? So it's the percentage of solids that we reject. If we're here over here, that would be 100%, so that would mean we were rejecting all the solids that are coming in. Not a good thing. If we were over here, then that would mean that we're rejecting 0% of our material. We're accepting everything, and we're not going to get any cleaning done if we do that. So we have to have a compromise. And the compromise typically is that we're going to reject about 20% of our solids, and we'll use cascaded cleaner sections in order to save some of the fibers. Now on the y-axis here is our separation ratio, and we're going to call that, and little m is going to be the mass flow of a contaminant. So if we have ink and we can magically understand what the flow rate of that ink is as a solid or sand, we've got the mass flow rate of the sand, let's call it sand for our example, in, minus the mass flow of the sand in the accepts stream, divided by the mass flow rate of the sand in to our cleaner body. So basically the separation ratio is telling us what fraction of the contaminant that's coming in is rejected. Okay, because the mass flow of sand in minus the mass flow of sand in the accepts is really the mass flow rate. This numerator should be is another way to put it is mass flow rate of the rejects, the contaminant in the rejects. Remember now, these m's are mass flow rate of the contaminant. So the separation ratio tells us what percent of the mass of the contaminant is going to the rejects. Up here would be 100% of the contaminant going to the rejects, and down here we'd have 0% of the contaminant going to the rejects. Of course we want it to be as high as possible, but of course we know that for the production rates and the consistencies and the operation variables that we have, we're not going to get 100% separation ratio. So the compromise is this. what we do is we pick a reject ratio, and it's typically around 20% as a ballpark estimate. If you look, this curve right here shows you that a typical separation ratio as a function of the reject ratio. So if we come to about here, 20%, what you notice is that our separation ratio occurs is about maybe 70 to 80%. So basically that's what the compromise is. We're going to reject 20% of our total solids, mainly fiber, and that will get us up high enough on this curve. If we start to reject more and more rejects, then we don't get as much bang for our buck. So you see this curve is kind of tailing over. So, and we also have the issue about how much fiber we're sending to our reject streams. That's not good. So we make this compromise, and we usually operate around here. Okay? This dashed line is just a control line that just shows us, well, if we just had a pipe split, we had no separation based on centrifugal forces or anything, then we would just we would have a separation ratio that's equal to the reject ratio. Okay? So that's just if we had a pipe, and the pipe had a Y in it, and then that Y would just, the volumetric flow rate or the mass flow rate of the solids would just give us an equal distribution of contaminants. All right, now we've talked up to this point about low consistency cleaners. So those are cleaners at around the 1% consistency, and we're rejecting about 30%. I want to now discuss high density cleaners and through flow cleaners for lightweight contaminant removal. This is a picture of a high density cleaner. And the high density cleaner, remember, these usually are put right after the pulper, and they're used to remove large contaminants like bottle caps, big pieces of glass, big pieces of metal or staples. And here's the feed. The feed comes in here. You see a pressure gauge. The feed pressure is important. The material starts to spin. And what happens is the large contaminants, let's say the marbles in this case, the marbles go to the outside, down to the outside of the wall, and then down this way. Okay? And then the good fiber and the other stuff, the good fiber, and there's also some contaminants in there, but the good fiber spins around, and then it comes up this way. Okay? And there's our accept. It goes on to probably coarse screening. Now, at the bottom of this high-density cleaner, we're showing a 2-valve system, and this valve system is going to basically intermittently reject material. So in regular operation, this valve will be open, and those marbles, let's call them marbles in this case, those marbles are going to fall down, they're going to go through this open valve, and they'll just settle down here. Now, during operation, this entire vessel is filled with material, but the heavyweight material lands down here at the bottom and settles down and stays there. This valve is normally closed. Now what happens is usually there's some type of level gauge, or these things are on timers. And so at a certain point, this valve will close, this valve right here will open, and the rejects will be flushed out the bottom of this chamber. Okay, at the same time, there's material going through this, but it's pretty quick. So the heavyweight stuff is just kind of falling down here and kind of waiting here just for a brief second. And then what happens is that valve, once that material is dumped, that valve closes, that valve opens, and we continue the process again. And those marbles will fall down in, and they'll collect there. And then again, we will close that valve and open that valve and flush. So that intermittently occurs. So again, this is a large diameter piece of equipment. The flow rate through it, the consistency is pretty high. The material that we're trying to remove is pretty easy to remove, and that's the nice thing. We're trying to remove huge pieces of glass that have high density. They're going to separate very easily, so we don't need to have low consistency or very high centrifugal forces. We just need something that's pretty robust, that's not going to plug, and that will get rid of some of the big contaminants. All right, now the other cleaner that I wanted to show you was the through flow cleaner, and this is one of the ways to remove lightweight materials like waxes, plastics, styrofoam, things like that. It's called a through-flow cleaner because all of the flow goes through the cleaner. There's no reverse flow here. What we have is the feed coming up the top, and then it curls around and it starts to rotate. And that rotational action now, what it will do is it will cause the fibers to go to the outside and the heavyweight contaminants to go outside. But what its intended purpose is that the lightweight contaminants, the low-density material, will stay in the middle. And when it stays in the middle, it's going to go and hit this receiving tube. It's hard to see, but there's a little receiving tube here right through the middle, and that's our rejects. And so the styrofoam and the wax and the plastics and the adhesives, the stickies, all those bad things are going to come right in the middle, right through that tube and out. Now the good fiber and the other materials are going to go towards the wall. They're going to go around this receiving tube to the outside, into this cup, and then out here, and that's called the accepts stream. So you've got a same principle, centrifugal force separating things, but now we're just going to take the middle stream and use that as the rejects. Okay? Now, I haven't mentioned, but you can pipe up these cleaners in many different ways. So you can have the accepts at the top, the rejects at the bottom. You can have an accepts and a rejects at the top. You can have reverse flow, forward flow only. There's many different ways, and you can go to the books and see them. The point here is that what needs to be done when the cone is designed, the design needs to take into account that the reject flow should be smaller than the accepts flow. So those ports need to be smaller for the rejects. And you can have combinations of cleaners where you're taking an accept stream out, a lightweight contaminant stream out, and a heavyweight contaminant stream out. So there's all different styles and ways to get about it. Designers can be very clever. In many cases, that cleverness pays off. In other words, you get rid of high-density contaminants and low-density contaminants. But it usually costs more to make that cleaner and to buy that cleaner, and also the more complex the cleaner is, the more likely it is to have operational difficulties, perhaps plugging. Okay, I digress. The through-flow cleaners are also piped up in banks. They're low consistency. And this picture right here will show you a bank of these cleaners. In this case, let's just see here. This pipe right here is the feed header. So that pipe right here is the feed header. And then you can see that feed header feeds this cone right here like that. And then
Richard?
Yes?
You can use the up arrow to go back.
Oh, okay, thank you. This pipe right here is going to be the accepts header. So that's the accepts header right here. And you can see that the accepts come from the side of this cup and then out into this accepts header. And then the reject port are right here. You can see them down here. And there, again, we've got a trough, and the rejects are being shot into this atmospheric trough. And I should mention right now, we've seen two cases where we have atmospheric troughs and the rejects are just sent to atmosphere. Why do you think that we have atmospheric conditions right here and we're just spitting it out into the air? Well, the reason why is that because the rejects ports usually are small, and there's the smaller the opening, the more likely that we get pluggage. Okay? So you can imagine that if we wanted to control the pressure in that rejects port with a valve, and that valve is even more of a constriction to flow, we would have more likelihood of pluggage. So we try to avoid valving on the rejects, and you'll see some that have it, but we try to avoid the valving on the rejects because it's just a place where we can get a lot of pluggage. All right, now I want to kind of talk about what are some of the parameters that influence the effectiveness of a centrifugal cleaner. We can kind of break them down into stock characteristics, cleaner design, and actually cleaner operating variables. So stock characteristics include fiber type and contaminant type, and we'll talk more about that in a little while. Cleaner design. There's a lot of different variables that cleaner manufacturers have in order to alter the effectiveness of the cleaner. And body diameter is one. Feed inlet configuration, at what angle that fluid's going to come into the top, for instance. The accepts diameter port, and for that matter, the rejects diameter port. The cylindrical section height, so usually these cones have a cylinder for a portion of it, and then they taper off down at the bottom, let's say. The cone angle, the angle of taper. Spiral grooves in some applications on the inside of the cleaner body. The reject rate control method, and that's fixed orifice and back pressure. So we talked about the fixed orifice is used so that we don't plug the cleaner. All right, so what are some of the operating parameters that affect hydrocyclone cleanliness efficiency? Now, let me mention cleanliness efficiency is another way, and I just put this down here, I think because it came out of the book, rather than the other definition we use. Cleanliness efficiency is the concentration of contaminants in the feed minus the accepts divided by the concentration of contaminants in the feed.
Would you like to write that on the document camera?
Oh, yeah, I think I would. Let's do that. So, is it on?
Yes.
Okay. So cleanliness efficiency is pretty convenient.
Zoom out, go to wide.
Zoom out, go to wide.
It's a wide button, yeah, there you go. Use one of the markers that's there in the cup.
Okay. Cleanliness efficiency is, and I'll just use S sub I for inlet minus S sub A for accepts divided by S sub I, and we'll multiply by 100%. Now, the S is the concentration of contaminant, and we usually use the measurement ppm, and that's parts per million. And basically, what we do is we typically make a hand sheet and look at the area covered by dirt divided by the clean area of the hand sheet, and we make a ratio of that, multiply by 1,000,000, so ppm. And so that's the important thing here. So this is actually, I would say, is different than the previous definition I used, because cleanliness efficiency doesn't tell you what percentage of contaminants go to the rejects like the other one that we used. Cleanliness efficiency, what it does is it really just tells you how clean the accepts are relative to the feed. Okay. And the thing that the cleanliness efficiency equation misses is the fact that it doesn't have the mass flow rate of the contaminant and the mass flow rate of the contaminant in the accepts. It just has the concentration, and so what it skips is if we were to take these concentrations and multiply them by the oven dry flow of solids in each of these streams, then we would have really the percentage that's going to the rejects. But because we omit the mass, oven dry mass flow rate of the inlet and the accepts, this is just a relative quantity that relates the accepts contaminant concentration to the inlet. It's not a mass balance, not based on a mass balance. So for instance, we could have a very high cleanliness efficiency, but if we're only accepting a very small percentage of our solids coming in, then that cleanliness efficiency is somewhat misleading. Okay. So let's just, cleanliness efficiency is, though, related to the efficiency, the removal efficiency. So pressure difference actually can increase or decrease the cleanliness efficiency. If we take the pressure and boost it up and have the same accepts pressure, then what we can do is increase the velocity inside the hydrocyclone, increase the forces, and actually increase the efficiency. However, if that pressure difference is increased by opening the accepts valve, then we're just accepting more material and we can decrease the cleanliness efficiency. Okay, so what we're looking at is increases in these variables and how that increase affects the cleanliness efficiency and the sensitivity of the cleanliness efficiency to that variable. So the sensitivity is very high. Volumetric flow rate, for the same reasons that the pressure difference. If we increase the volumetric flow rate into the cone, then that causes our fluid to spin faster. That can increase the cleanliness efficiency. If the volumetric flow rate is increased because we open the accepts valve, we can get a decrease in cleanliness efficiency. Now the cyclone diameter, if we increase the cyclone diameter, then that will decrease the cleanliness efficiency. In other words, the centrifugal force is related to related to how small the diameter is, because the smaller the diameter, then the faster that particle has to change direction, so there's more centrifugal force to it. So as the cyclone diameter gets smaller, our cleanliness efficiency as the diameter gets smaller, the cleanliness efficiency increases. As the diameter gets larger, the cleanliness efficiency decreases. And there's a very high sensitivity. Now consistency is another one. As our consistency increases, there are more fibers in the system. And those fibers prevent the contaminants from freely separating themselves from the fiber matrix and going where they need to go, independent of the fibers. So the higher consistency, there's more of a web or a resistance to the contaminants traveling away from the fibers. So we're causing a resistance here. So the higher the consistency, the decrease in the cleanliness efficiency, and that sensitivity is high. Flake content is the same way. Flakes are unpulped fiber bundles, and those will also cause a resistance to the contaminants moving independently of the fibers. So the more flake we have, the lower the cleanliness efficiency, and it's a medium sensitivity. Temperature, if we increase the temperature, then the cleanliness efficiency increases. Okay, and that's just a general rule of thumb. This is a low sensitivity. What's happening here is we're saying that as we increase the temperature of the fluid, its viscosity, or the resistance to flow, decreases. Then the contaminants can travel through the water easier, and so the temperature could that temperature effect could increase the cleanliness efficiency. Now you could come up with different scenarios where temperature might even decrease the cleanliness efficiency, but we're getting to very subtle nuances. For instance, if we change the temperature of the system, then the density of the water might change slightly, and the density of the contaminant might change slightly, and the density of the fibers could change slightly. So it's actually these density differences that cause the separation, and so if temperature has an impact on density, we could see a change in the cleanliness efficiency. The reject rate, of course, that the more we reject, like that characteristic curve we looked at, the higher the cleanliness efficiency, and that's a medium sensitivity, but it's a medium sensitivity if we operate within the general reasonable range that is expected with cleaners. And then flushing flow, I didn't mention this. Some cleaners, especially the high consistency cleaners, they have a flushing mechanism where we add water to the bottom of the cleaner so that it won't plug, and also to just help the rejects get out of the cleaner system. Well, that flushing, actually that water pushes the rejects up towards the accepts port a little bit. And so if we flush with too much water, then our cleanliness efficiency will decrease. And again, the flushing flow is usually for these high consistency, large diameter cleaners. All right, so those are operating variables. Now we can take a look at the effect of particle properties on separation. The first thing we'd say is that particles with large density differences with respect to water are removed more effectively. So for instance, if you have a very, very dense contaminant, it will be removed effectively. Or if you have a very, very light contaminant, things like styrofoam with a low density, that will be removed effectively. Now, particles with a density near 1 gram per centimeter cube may separate from fibers. That's interesting. So basically what's happening here, 1 gram per centimeter cubed is the typical density of water. We can have a separation of the density of the we can have a separation of the contaminants from the fibers in the water if the density of the contaminants changes with temperature, or if the drag coefficient, how easily that contaminant flows through the water, is different than the fibers. And we'll get into that a little later. I'm just kind of going over the general things. Larger particles at the same density will be removed more effectively than smaller particles. What's happening here is that the centrifugal force depends on the total mass of the particle. So even if it's dense, but it's too small, then it won't be separated. So it's harder to remove the smaller contaminants than it is the larger contaminants. And we already discussed that with a high consistency cleaner with a large diameter and the large contaminants right after the pulper, those are pretty easy to remove. We don't need very high G's, centrifugal forces, to remove those. But for the low consistency cleaners, where we're trying to remove some of the smaller contaminants, we need to have higher G forces. Okay, particles of the same density but with favorable hydrodynamic shape separate more effectively. As an example, a sphere is going to be separated from fibers better than a flat plate. You can imagine that the sphere can travel through the water in a more aerodynamic way than would a flat plate that's like a sailboat. So a sphere can shoot through the water much better than a flat plate. And then this is just C sub W is a drag coefficient, and A sub P is the projected area. So this is basically the resistance of the particle flowing through water. All right, our last topic I want to just talk to you about is I want to just kind of do a force balance on a single particle in a hydrocyclone. And in this, we'll just kind of touch on what are the different forces that are acting on that particle, and then that kind of gives us a better feel for how things are separated and what operating and particle characteristics affect the separation. So in our diagram right here, here's our particle, and we've got, if you can imagine that the cleaner body is up like this, the rejects is towards the bottom, the axis is towards the top, for instance. Let's just say that this line right here is the center of our cleaner body. We've got a particle right here, and that particle can move in 3 directions, right? It can move in the radial direction, which is indicated like this with this line, so the radial direction. That particle can move up and down in the cleaner body. That would be called the axial direction. And then the other thing to think about is that that particle is spinning, and we're going to be spinning around the center of that hydrocyclone. So we'll be spinning like this. That's called the radial direction. So we can have motion in all 3 of those directions. Now, in the what causes the motion in those directions? Well, forces do. Forces applied onto this particle will actually have it cause it to move. So what are the forces in the radial direction? These are the forces that are causing the particle to go towards the wall of the cleaner. Well, we've got one force, F sub C. That's the centrifugal force. We're going to call it the net centrifugal force. And everyone remembers as a child that you could take a bucket of water and you could spin it around like this, and the water would stay in that bucket as you were spinning it. And that is a reflection of centrifugal forces. So those centrifugal forces are causing that particle to move towards the wall. And then this F sub D is the drag force. And what we know is that when anything is moving through a liquid, the viscosity of that liquid actually pulls on that particle. So when you're swimming through a pool, there's a resistance for your body to go through that pool. That's the drag force of the water. It's the force that the water is imparting on your body, resisting it from just actually moving very rapidly through the water. So we all know that we can run through the air much faster than we can swim, and that's because the viscosity of air, the resistance of flow of air, is much less than of water. So in the radial direction, we're going to balance the centrifugal forces and the drag forces. In the axial direction, we're going to have the net gravitational force, and this is usually extremely small, F sub g. And then we'll also have a drag force, okay? But basically, with this one, the fluid is going to be moving with the particle is going to be moving with the fluid. And so these forces right here and the motion of this particle depends quite a bit on how the accepts valve is positioned and the rejects port or valve is positioned. And then the last one is the tangential direction. And for this, with this, that we're talking about the tangential the tangential direction like this, spinning around the axis, and that we're going to assume that the particles move along with the fluid. So the fluid starts to spin based on that inlet tangential flow at the top of the cone, and that this particle is just going to move right along with the fluid. All right, now what we're mainly interested in talking about is what causes these particles to move towards the wall and what causes relative to one another. So we can think about a particle moving towards the wall, or we can talk about a fiber moving towards the wall, or even water moving towards the wall. So what we'll do is one-dimensional analysis of a single particle in the radial direction. And again, we've got the centrifugal force coming this way towards the wall for a high-density material, and then we've got the drag force. That's the force of the liquid as that particle is moving through the liquid medium. All right. Now, what we start off with is force is equal to mass times acceleration. On the right-hand side of this equation is all our forces. So the sum of our forces is equal to mass times acceleration. So we've got two forces that we're going to talk about, centrifugal force and drag force. They act in opposite directions. So the centrifugal force is acting to the right, which is a positive direction. The drag force is acting towards the left. That's a negative direction. And those two forces are equal to the mass times the acceleration. The acceleration, this term du dt, acceleration is the change in velocity over the change in time. So mass times acceleration. Now what we're going to do is we're going to assume that the time for the particle to reach a steady state velocity is very brief. So the particle comes into the cone, the forces act on the particle, and very quickly what happens is the centrifugal forces start pushing that particle towards the wall, and the drag forces increase as that velocity of that particle increases due to centrifugal force. And what happens is this particle will accelerate in this direction until this force equals this force. So that's going to be one of our assumptions that we're going to work on. We're just going to say that this force is equal to that force, and they're in equal opposite directions. So this particle is moving at a velocity towards the wall that is constant. So we put 0 here because the acceleration is 0, and we get this. So what we're saying here is that our centrifugal force is equal to our drag force, and that equilibrium is set up very quickly. Okay? Even though these forces are balanced, we still have a velocity towards the wall. That's important to remember. Okay, so what we'll do now is we'll introduce this particle slip velocity, U sub s. That's the velocity of water minus the velocity of the particle. Okay, so when we're trying to separate material from each other, what we're interested in is that the particles and the fibers, they should be moving towards the wall faster than the water if they're of higher density. So right here we have an expression for the net centrifugal force, okay, and you can see it's got the density of the particle, and here it's U sub t. That's going to be the tangential velocity of the fluid. So that's the velocity of the fluid spinning in the tangential direction. R is the radial position, and then this is rho sub, and we've got a minus rho sub L. That's the density of the liquid, and then we've got the tangential velocity squared in the radius again. So what this is the net centrifugal force. So you need to understand that the particle has to be more dense than the liquid in order for there to be a separation. If the particle has the same density as the liquid, then the centrifugal force is going to be the same, and then the liquid and the particle are going to be moving to the wall at the same velocity, which we don't want. So this is the net centrifugal force. It's the different, and then we multiply that by V sub p. That's the volume of the particle, and that has to equal our drag force. And then we have an expression for the drag force. The drag force is 1/2. Now it's going to be rho L. That's the density of the liquid, times u sub s squared. Now that's going to be our particle slip velocity, u sub s, and we're going to square that. So the drag force is proportional to the square of the slip velocity. And then a sub p is the projected area of a particle. So for instance, if I have a sphere, the projected area of that sphere is actually a circle. If you look at it straight on, and you'll see the projected area is a circle. And then we have c sub d, and that's the drag coefficient. And that we can estimate from literature values or try to measure, but it's extremely difficult to measure. But basically, this drag coefficient is characterized by the particle shape and size, and also some of the fluid flow features. So that's our drag coefficient. And the higher the drag coefficient, the more force, more drag force there is. So we've got this set up. The net centrifugal force equal to the drag force. Now, we'll take this equation and we will solve for u sub s. Okay? So u sub s is equal to the square root of all of this. And that's for the radial direction. And remember that it's that slip velocity that tells us how quickly the particle is moving towards the wall relative to how quickly the water is removed towards the wall. Okay, so here's our equation, u sub s here. And let's just kind of look these pictures. Right here we've got two arrows. One is orange and one is white. Okay? So for high slip velocity, this orange arrow right here is long, and so that's going to be the velocity of the particle. And the white right here, that small arrow right here, it's hard to see, that's the velocity of the fluid. So for high slip velocity, the particle is going to be moving towards the wall much faster than the water. We'll have high US, and then that particle will be rejected. Now for low US, now here we've got the particle, it's still moving towards the wall, as is the water, but the difference between the two is small. So we have a low US, and for that reason, that particle would mainly be remain in the X upstream. So we can imagine that we would hope that fibers have low US and high density contaminants have high US. Okay? Now, what I'm going to kind of summarize here is that if we come back to look at this equation, we want high US, right? We want high slip velocity. Well, we see here that high UT, or tangential velocity of the fluid, will increase the slip velocity. So we want to have the fastest rotating fluid that we possibly can have to get higher slip velocity. What you notice here is R, the radius, is in the denominator. So the smaller the radius that we have, the higher the slip velocity. So again, that's showing us that the smaller diameter cones are going to have more centrifugal forces, and that will cause higher centrifugal forces, and it will cause better separation. Okay, the particle density, rho sub p, right here, that's in the numerator. So the higher the particle density, the higher the slip velocity. That's good. And it's not really just the particle density. It's the particle density minus the liquid density. So it's this relative density divided by, actually here, the liquid density. So this term needs to be as high as possible to get the slip velocity high. And then the last thing we see is here, 1 over CD. So the drag coefficient, the resistance of that object to move through the liquid, that has to be as small as possible for our slip velocity to increase. Okay? So again, this equation right here gives us a lot of information about how cleaners can be effective. And it's got particle properties, CD and rho p, and it's also got operation properties like U sub t. There's another term, VP over AP. That's a shape factor, and so the shape of the particle also makes a difference. So you can see that there's a complicated set of variables that all come into play to find the removal efficiency. Okay, so that's the lecture for today. I'm just going to quickly summarize. There are several types of cleaners. Okay, we talked about the high consistency cleaners that are usually seen after the pulper. They have large diameters. They don't have very strong forces, but because they're removing big, gross contaminants like big pieces of glass and metal, they work pretty effectively. They don't reject much material, less than 1%. Then we have medium consistency cleaners. We didn't talk too much about them. And then we have the low consistency cleaners. We did talk about them quite a bit. The low consistency cleaners usually are smaller in diameter. They have much higher G forces or acceleration, gravitational, centrifugal forces. And they're also, typically we reject about 20% of the material and cascade these in order to get proper effective separation. The objective of the cleaners are to remove high or low density contaminants, but we know that that's not the full story. We also have particle shape and operating conditions like consistency to consider. In order to operate effectively, we must reject some material, especially for the low consistency cleaners. So I mentioned to you that we reject about 20% of our material. And we use cascaded operations so that we can save fibers. We don't lose all 20% of our fibers rejected from a primary stage. And then finally, we saw from fundamental view that several forces and operational variables and particle characteristics all combine to determine the effectiveness in removal. So there's, although it's a very simple piece of equipment and there's no moving parts, there's a lot of things going on there. Lots of different contaminants, lots of different operating conditions, and all of these combine to make to define the effectiveness of the cleaner. And appreciate your attention, and that will conclude our cleaner lecture.